Okay. Yeah. So if you see the schedule we have right now, share the desktop. So you see our midterm is on the 18th, right? So that's going to be 2 weeks later. Right now we're on 6th. So we were supposed to be talking about the sedimentation and filtration principles, but we already did that last class. So we're going to cover water softening this class. So this will leave an open lecture for next Tuesday before the fall recess. So now here's the thing. I receive maybe 1 or 2 emails from you about how to prepare for the exam. So do you want the lecture of next week to be a review session, or should we move ahead to
Yes,
start?
let's make it a review session.
We should definitely do a review.
So if you do review session, then I need some input from you. So you can send me questions that you have or the homework problems. So let me just clarify this a little bit more. So for the exam, there won't be concept questions. I won't ask you to write down the definition of something. Okay, so that's not the idea. So mainly it's gonna be something like calculation problems, like the homework problems. So as I said, if you can work out the homework problems without spending a lot of time referring back to the textbook or the notes, then I think you should be okay. But now we just want to make sure that you understand the homework problems or the problems with like calculation problems we show in the class. So you can send me by email, or if you want that to be anonymous, I can also send you a Google form. So you don't need to put your identity in there. So you won't be feel like weird to tell that you don't know let's say some of the fundamental things. Okay, so I can send you that Google form, and you can just type in whatever problems or questions you might have, and then we can go over that next Tuesday. Is that okay?
Yeah, that sounds pretty good.
Okay, yeah, that's good. So in that case, I think next Tuesday you also have your homework due. So what I'll do is that after you submit the homework, I'll also upload the example solutions for all of the previous homework problems, so you can start to get prepared for that. Okay, I mean I can upload maybe all the homeworks except for this one, maybe today, so you can also get to prepare earlier. All right. So this is about the schedule. All right. So let me see. And then we can also spend some time to talk about the, let's see, where is the share screen? Okay. Yeah, to spend some time talk about the team project. So as I said in the like the introduction class, so there will be a team project. So that I think that corresponds to 10% of your, or 10 points of your total score. So we can maybe just briefly introduce what this project will be about. So I'm still finalizing the detailed like terminologies in this project, but that main idea is that you're going to form groups. So each group will have 2 people, right? 2 students. And then you will identify a environmental problem. So it can be problems that's happening in the air or in the water or the solid, right? The solid waste. So right now we have been mainly covering water, but later on after the midterm, we're gonna start to cover the air pollution. So there are some quite emerging issues with these like new environmental problems, like the PFAS. We covered a few classes before, and then there's microplastics, which is a new issue, right? Air pollution, there can be some dust problems, like when we discussed about the drying of the Great Salt Lake, right? So you identify one environmental problem, and then also talk about basically analyze the location, right? Basically, is that a regional problem? Is that a global problem? Like carbon dioxide, that's a global problem, right? You also identify the time period, whether that's talking about future, talking about right now, or in the past, let's say 200 years ago, there are some environmental problems. So more importantly, I want you to quantify, like do some quantification regarding the source and the impact. For example, how much of these pollutants are being generated and dumped into the environment, right? What are the major sources? Are they coming from residential area? Are they coming from industrial, or are they just natural sources coming from volcanoes, right? We know volcanoes are generating sulfur dioxide. They're just pumping the sulfur dioxide into the air, and then they're actually acting as a net cooler of our climate. It's always generating a lot of these aerosols containing sulfur, right? They can reflect the light better. So also, I want you to add a section about how the climate change might influence this issue. So there can be, let's say, there will be more frequent, let's say, extreme weathers, or there is an overall increase of the temperature, or maybe these conditions will not impact these environmental problem at all, right? For example, if you think about the air pollutants coming out of the wildfires, then if you have more extreme conditions, extreme weather conditions, you are going to have more wildfires and therefore more air pollutants, right? And then we'll discuss, or you will discuss what are the engineering methods to solve or mitigate these issues. So as I said, it's going to be a team of 2 students. So we have 14 in total, so there will be 7 teams. And so we will have the presentations during the last week of our class. So that's going to be November 29th and December 1st. So each team is going to present for 10 minutes. So on 29th, there will be 4 teams. December 1st, there will be 3 teams. And then apart from the presentation, there will also be a somewhere like a report or essay associated with this presentation. So regarding the team assignment, I think at first class, I was asking whether you want to form teams by yourselves, but then after some thought, maybe just thinking about mixing the whole classroom better. So unless you have a strong preference of teammates, okay, you can email me about that. I'll try to accommodate it. Otherwise, I'll just assign the team randomly. I'll just use some random number and then pair the 7 teams. Okay. Any questions about the team project? We good? Okay. So I'll post more detailed informations about these team project next week. All right. So now, if we do a quick recap of our last class. So last class is a recorded lecture. So hopefully you can get most of the things in there, right? So last class, we mainly go through 3 steps in the water treatment process. We cover the coagulation, flocculation, right? So we basically, let's say, discuss how the mixing, like the speed of the mixing and the residence time might affect different processes, right? So we said that coagulation will require faster mixing and then a shorter residence time, because we want the coagulants to dispense or get dispersed in the water more rapidly, right? We also want a shorter residence time because we don't want to break those flocks. And for flocculation, it's the opposite, right? We want a slower mixing and longer residence time so we can get the particles to settle down. And then we discussed the sedimentation basin. So basically, sedimentation basin is just trying to remove particles based on gravity, right? So there are some calculation about this special settling velocity, which we call as the overflow rate, okay? And then there's also this discussion about the sand filtration, where we build these filters and then just let the water to settle down. And that's also associated with the velocity. And we call that velocity as the loading rate, okay? But for both of these systems, we have a pretty straightforward equation to describe the design parameters. That is V equals Q divided by A, right? So the Q here is the flow rate of the water, right? A is the surface area. Okay, so basically, for example, for the sedimentation basin, what we will do is we'll specify a overflow rate. That is kind of like the critical velocity of the suspended solids that can be settled, right? With that velocity specified, and if you know the flow rate, right, you can calculate what is the surface area. So the same thing for the rapid sand filter. If you know the let's say if we specify a certain velocity, right, for the particles or for the water to settle down through the filter, then with the flow rate and with the flow rate, you can also calculate the surface area of the sand filters. So there are some practice problems with that too. That's actually in your assignment. Okay. So now this class, oh yeah, here is actually a quick question. So here we have a sedimentation basin that was designed to deal with a fixed overflow rate. Okay, it was found that the total flow rate of the water become twice of the original design. So how should we change the surface area of the sedimentation basin? Just by using the equation we just covered. Let me create a.
It's, oh,
Yeah. Anyone trying to say something?
oh yeah, I was asking, so if you're doubling the, if you're doubling that rate, I guess you're like halving the area.
So if you just look at the equation here again, right? So the overflow rate is calculated by the flow rate divided by the surface area, right? So we said that it's designed with a fixed overflow rate. So the fixed overflow rate means that we want to settle the same size of the particle, but it turns out that there are more water flow going through, right? To maintain or to make sure that the particle of the same size can still get settled, we should make the sedimentation basin larger, right? So basically, this overflow rate is locked, right? If you double the flow rate of the water, you will double the area of the basin. Okay, does that make sense?
Yeah, I didn't realize that it was static.
Yeah. So maybe I should circle this out, the fixed overflow rate. Yeah. So I think this is just some general application of this equation. So normally there will be some more calculations. Let's say it'll give you the exact flow rate of the water and then give you the overflow rate, and then you can calculate what is the surface area for the sedimentation basin, right? So this is more like a design problem. All right. So then again, this is an overview of the water treatment facility, right? We showed this picture in our last class and the class before, right? So just to quickly go through this process again, we said that there is screening, right, to remove the larger particles. And then we covered the coagulation, flocculation, sedimentation basin, and then sand filtration, okay? So, and then for the chlorination, let's say here, or the fluoridation, we won't cover that in this class. I think that's just some extra reading for you. So it's not going to be in the exam either, right? So if we didn't cover that in class, we won't test those. So the rest of things are just pumps, right? Or the water towers. They're more like physically storing or handling the water, right? Because in order to let the water to flow through all the devices, you have to give it a speed, right? So that will need pumps. So in the water treatment facility, basically you lift the water to a higher altitude, right? So they can just flow by gravity and then create that flow to go through all of these devices. And same for the water tower. So the water tower can give you that and potential energy, right? So they can flow down and then get delivered into the residential area. Okay, so this is about the surface water treatment, right? So then this class, we're going to learn something new, that is the water softening. Okay, so you probably wonder, because in this system here, we didn't show softening, right? So as I said, the water softening is mainly dealing with underground water. So the reason is that the softening is mainly trying to deal with the calcium ions and magnesium ion, or so on, okay, some other ions too. So these ions are actually minerals. So the water that has a longer contact time with minerals will have a higher concentration of these ions. So because of that, the surface water, since the river is always flowing, right, it doesn't have that long enough time to pick up these minerals. So that's why for the surface water, let's say for river water or for lake water, these ions concentration are relatively low. But if we're talking about the deep well water, right? So for the water that we get from the basically underground, then those water are going to have a longer resonance or longer contacting time with the minerals. So their these mineral ion concentration is going to be higher. So basically for the softening, it's more specifically designed for underground water. Okay, so this you can also see the difference between the surface water and the groundwater. I don't know if you have seen a well, like the well for water in person, right? Or you probably see that in movies. So normally when people, let's say, use a bucket, right? They put the bucket into the well and take the water out. The water is very clear, right? So it's even drinkable. So people never do more processing, or they probably won't, right? So they can directly drink it. Maybe they will boil it, right? But the water has a very good quality, so it won't harm the health. But the thing there is that there are probably too much of these minerals here. Although their health impact is not in a conclusion yet, because you see some of the when you go to the supermarket, right, to buy water, some of them will specifically say that, well, this is mineral water. It's your body needs that, right? But if is too much mineral a good thing, right? There are some stories saying that if you have water that has too much calcium in there, you might form kidney stones, right? But there haven't been a conclusion regarding how these minerals might affect your health. But with this too high of mineral concentration in your water, in your pipes, then we may have issues that's associated with the scales, right? So for example, if you have a water that has a high hardness, which means that these ions concentration is too high, then you can't properly wash these glasswares. So if you just wash it using the tap water, after they dry, they're going to have these white scales. The same for the kettle. After you boil the water, you're going to form these residues, right? So the faucet, right? Showering faucet, and then these scales here. But what's more damaging, I would say, is that these minerals, since they are existing in the form of bicarbonate. Okay, so we said bicarbonate is very easy to get dissolved into water, so they can have a high concentration in water. So these, at the same time, these bicarbonates unstable. So if you have a temperature fluctuation, let's say if it gets warmer, then these minerals will just get dissociated, right? They're going to form calcium carbonate, which is a sediment, right? So they can just get accumulated into the pipes. So that's why for some of the households, let's say, if you, especially because nowadays we have the cold tap water and let's say the hot tap water. So for the hot tap water, if you use that for a long time, right, you can feel the water flow is getting smaller and smaller. Sometimes you can hear the sizzling sound, right? That is because some of these minerals just get deposited in the pipes, simply because the temperature is too high, right? They just get dissociated. So we mentioned something about the coal-fired power plants before as well, right? So we said that the water or that's getting evaporated into high temperature vapors are ultra pure water. So we cannot allow any minerals inside. Otherwise, you're just going to block the pipes inside, right? And then there will be explosions. So that's why there is a very high standard for the water to be used in the coal-fired power plants. Okay. So to deal with this problem in residential, let's say in houses or in apartments, I don't know how many of you have seen this before or how many of you installed this at your home, right? So this is what we call the water softener, right? Okay. To use that, you also need salt. And actually this salt here is just sodium chloride. Okay. So we periodically put the salt inside, and this is actually using some resin to deal with the hardness ions, which is, we're going to cover that later on in our class. Okay, so here I have a short video just talking about the, in general, what water hardness is, right? So we can spend some time to go over that.
hard or soft? How am I supposed to know they both look exactly the same? Hey there guys, Sapna here for D News. From the outside, all water is seemingly the same. Clear, mostly flavorless, 2 hydrogens, 1 oxygen. But once you get past the basics, water is actually pretty versatile. It can be distilled or filtered, tap, bottled, and if you're really fancy, there's water marketed as kosher, organic, or Kabbalah. But did you know water can also be hard or soft? No, this isn't to describe how the water actually feels. It has to do with its mineral content. Water becomes hard when it has a higher than normal concentration of minerals, primarily calcium and magnesium. Water picks up these minerals from rocks and soil as it flows through rivers, wells, or other waterways. Soft water, on the other hand, has a low mineral content, either because it has not yet flowed through rocks or wells, like rainwater, or because the rocks it has come in contact with have little to no soluble minerals. But that isn't to say that there's a set amount of hard and soft water on Earth. Because of the hydrologic cycle, our water fluctuates between hard and soft. For instance, water that lives in oceans or streams tends to be hard because it's already picked up minerals. But when this water evaporates and later becomes rain, it leaves those minerals behind and becomes soft. It's important to note that water is not just hard or soft. It's a spectrum, with water becoming more hard as its mineral concentration increases. The United States Geological Survey classifies soft water as anything with less than 61 milligrams of calcium carbonate per liter. Above that is moderately hard water, then hard water, and very hard water. According to the U.S. Department of Energy, almost 75% of U.S. homes have water that is at least moderately hard. Probably the best place to see the difference between hard and soft water is in the bathtub. Soap is primarily made of a white solid called sodium stearate, which, with the help of water, carries away dirt and oil. Normally, the components of soap dissolve in water, causing a good lather. But in hard water, the soap reacts with the minerals, forming insoluble compounds. For example, the magnesium in hard water reacts with the stearate to form magnesium stearate. This makes it more difficult to get a good lather in hard water. It also causes the soap scum you see on the sides of the bathtub. Hard water can also leave behind limescale, which occurs when water is heated or when it sits for too long and the minerals solidify as that water evaporates. As you may have noticed in your own home, limescale looks gross and it's really difficult to get off pots and faucets. To avoid this, a lot of people choose to soften their water. An easy way to do this is by boiling water, which causes the calcium carbonate to evaporate, leaving the remaining water soft. However, there is another type of hardness called permanent hardness that cannot be boiled away. Water becomes permanently hard when it flows through rocks with calcium sulfate, also known as gypsum, which cannot be removed through boiling. But despite its name, water with permanent hardness can be made soft. The most common way of doing this is by adding a chemical softener that filters out many of those minerals. But you may not be compelled to do this because beyond difficulties with bathing and some household chores like laundry and dishes, both hard and soft water are generally thought to be safe to drink, cook with, and bathe in, especially if the water has gone through a treatment plant, at least in the United States. However, some cities do choose to soften their water, removing some of these minerals at the water treatment plant before it even goes out to consumers. If you're curious whether the stuff coming out of your tap is hard or soft, take a swig. You can usually taste the minerals in hard water, whereas soft water is a little more flat and can sometimes taste salty. So that covers fresh water, but what about salt water? Why can't we drink it? Trey answers that question here. Got any more questions about water? Let us know in the comments and subscribe to D News for more.
Okay, so I think that's a nice video talking about like some generals. What are the water, what is the water hardness and where they're coming from, right? So let me share my screen again. Okay. So more technically speaking, I think in the video it says that these hardness ions are mainly calcium ions or magnesium ions. But actually, more specifically or technically speaking, these hardness ions are also including some other ionic species. So basically all of these polyvalent ions, polyvalent cations, because eventually when we talk about the residues, right, if we boil the water, right, the calcium carbonate or magnesium carbonate, so let's say ferric carbonate, right, and then barium carbonate. So they're all sediments, right? They can all settle down and creating this hardness problem. But the thing is that these two are the most important ones, mainly because their concentration is highest. So they just dominate these polyvalent cations that's discovered in the water. So that's why we mainly focus on these two types of ions. So technically speaking, people will need to quantify the hardness, what we call the total hardness of the water. So we use TH for short, right? So this TH means total hardness. Okay, so people will do these ionic measurements. Let's say we sample the water coming out of a river and then try to measure the concentrations or the mass concentrations of these different types of ions, right? And then the total hardness is just a summation of all of these ions. And then we need to be cautious about their units, right? Because we cannot directly use, let's say, milligram per liter, because these different ions or different metal ions, they have different molecular weights, right? So their contribution to the hardness will be different because eventually they're all forming these carbonate species. But the calcium ion is heavier compared to the magnesium ions. So if you're just directly summing their mass concentration together, they don't reflect what is the contribution of these two ions, right? So that's why we need to use the unit, let's say in mole per liter, right? Or millimole per liter, right? But more commonly, people use the unit of milligram per liter as calcium carbonate. So this is another equivalent unit, right? So you may recall for the alkalinity, right? When we talk about the alkalinity, right? Or the ALK. So we show that as a with the unit of milligram per liter as calcium carbonate, right? Mainly because we're trying to see how much hydrogen ions the solution can neutralize. And we're trying to find an equivalent mass concentration as calcium carbonate, because calcium carbonate can also neutralize the hydrogen ions, right? But why do we do this unit here? Okay, so it has to be associated with the treatment process of these hardness ions, okay? So what happens in the water treatment facility when we're trying to deal with these hardness ions is that we just let them react with the calcium hydroxide. Okay, so to deal with these minerals, right, because they are existing in the form of the calcium bicarbonate or magnesium bicarbonate, so they can react with these calcium hydroxide at a 1-to-1 ratio, right? And then you see basically these two ions are going to react with each other, right? They're going to form two water and then two, let's say, two carbonate ions. And then the two carbonate ions are going to react with the calcium, right, to form two calcium carbonate, and they're going to settle down, right? So basically these two, the calcium bicarbonate and the magnesium bicarbonate, they're just reacting with the calcium hydroxide at a 1-to-1 ratio, okay? So this is what we provide into the water to deal with the hardness ions, right? But then if you further look at what is the source of these calcium hydroxide, basically, people create that by dissolving calcium oxide in water, right? You form calcium hydroxide. And then where does the calcium oxide come from? It's coming from baking the limestone. If you just bake it, you get calcium oxide and carbon dioxide. Okay, so basically the raw material that each water treatment facility are going to buy, it's just going to be the calcium carbonate or the limestone. Okay, so if we show the unit of the hardness or the water hardness in the form of the milligram as calcium carbonate, then it's going to be easier for the, let's say, the water treatment facility manager to know how much calcium carbonate they're going to require to neutralize these mineral ions, right? If you, let's say, you have 1 mole of these hardness ions, no matter whether that's calcium ion or magnesium ion, then we know that we need 1 mole of the calcium carbonate, 1 mole of the limestone, right? We just need to buy 100 grams of limestone, bake it, and then put it into the water, right? So this is why we use this unit again to show the hardness of the water. Okay, so here I have another short question. Okay, so if we have a groundwater that has a total molarity of the calcium and magnesium ions of 2 millimole per liter, how much calcium carbonate should be used to soften the water? So this is kind of like the equivalent. Okay, so we're trying to convert that into the unit of milligram per liter as calcium carbonate. Any answers? Let me quickly create a poll.
Was that a calcium ion or a magnesium ion?
That's either calcium or magnesium,
Oh, okay.
or either. It can be a mixture too.
Yeah, we just can't see it on the screen anymore.
Professor,
Oh,
we
you
can't see your screen.
Okay, let me launch this pool first. Okay, I'll remove this web page. So then basically my question is, does it matter how much calcium ion or how much magnesium ion we have? So will the answer be different if we have, let's say, 1 millimole of calcium, 1 millimole of magnesium, or let's say 0.5, 1.5, splitting it into different concentrations? Okay, I don't know why this screen is always jumping up. Okay, any thoughts?
There's just like a conversion factor for millimoles per liter, right? Like,
So let me just quickly go through this again. Okay, so basically the way we deal with the hardness ions is just by, let's say, by acquiring the limestone, right? Bake it and then put it into the put it into the water as calcium hydroxide. Okay, so if we have 1 mole, let's say one number of the calcium hydroxide, we're going to require one number of the one number of the calcium bicarbonate is going to require one number of the calcium hydroxide, which eventually means that we're going to require one number of the calcium carbonate. It's the same for the magnesium bicarbonate, right? You need one number here, and then you need one number here. So now, if you see the groundwater already has 2 millimole per liter of these ions. Then how much calcium carbonate do we need to neutralize or to soften the water? I hope this way you get the problem a little bit more clarified. So if I ask you how much, like in terms of molar concentration, do we require to deal with these mineral ions? Do we need 1 millimole or 2 millimole or 0.5 or or 0.5? So yeah, I hope I explained a little bit better, but let's put in the pools first. Can you just put an answer right now? I want to show how many of you understand this, how many not. I'll give it maybe 10 more seconds. Okay, so we can stop here. Yeah, I see most of you got it right. Okay, so it should be C, okay, 200 milligram per liter. So the reason is, remove the pool. So the reason is we said that the calcium bicarbonate or this calcium ion are reacting with basically reacting with the limestone at 1-to-1 ratio, right? Because you have calcium bicarbonate, they're actually reacting with the calcium hydroxide. Calcium hydroxide is coming from the limestone. So they have a 1-to-1 ratio here. So if you have 1 mole per liter of calcium ion, then that's going to require 1 mole per liter of calcium carbonate, okay? If you have 1 millimole, right, you're going to require 1 millimole, okay? So the same thing for magnesium. If you have 1 millimole, you're going to require 1 millimole here. So now it really doesn't matter what is the split between these two. If you know the total concentration, or total molar concentration, you're just going to use the same molar concentration for calcium carbonate, right? Further, basically it means that you're going to require 2 millimole per liter of calcium carbonate. And further, we know that calcium carbonate has a molar mass of 100 grams per mole, right? So that would mean 200 milligram per liter as calcium carbonate. Okay, does that make sense? Any questions until now? So if we're good, then yeah, basically here we need to choose C. And this also shows that if we can measure what is the concentration, basically what is the molar concentration of these ions, then we can convert their unit, let's say millimole per liter, into milligram per liter as calcium carbonate. Okay, so here you have 2 milligrams, you just need to multiply that by 100, right? And then to get 200 milligram per liter as calcium carbonate. Okay, so this is, I would say, a shorter practice. So normally we're going to deal with water that has a more complex composition. Okay, so if you see here, we have a water sample, right? That has the following mineral analysis, right? This is the mineral analysis for the water sample taken from a well, right? You could imagine that there will be some hardness ions inside, right? And these are the different types of ions. Basically, you have the ferric ion, and then manganese, right? Ammonium, sodium, right? Potassium, right? Calcium, right? And then magnesium, and then barium. Okay, so it wants us to calculate what is the hardness of the water, right? So since we already have all of these different ions established here and we have their concentration, right? We can try to do some calculation. Basically, here it also notes that the concentration are showing in milligram per liter, right? So basically we need to convert all of these mass concentrations into molar concentration first, right? So similar to these ones, right? To convert it to millimole per liter, and then further convert it into the hardness as calcium carbonate. Okay, so we're going to use this equation here. The total hardness is the summation of all of these ions, right? And then basically we have these different types of ions included here, right? So we have the calcium, that's 67.2 milligram per liter, right? We need to divide that by the molecular weight of calcium, which is 40, right? 40 gram per mole. And then magnesium is here, right? You do 40 milligram per liter, divide by 24 gram per mole. And then there's no ferric ion, so we don't need to consider that. There's no ferrous ion. This is ferric ion, right? For ferric ion, that is 0.2 milligram per mole. And then this is 56 gram per mole. And then so on. But one thing you can notice from all of these different types of ions is that these concentrations are very low compared to the calcium and magnesium, right? So calcium and magnesiums are 40 to 70, right? But for the others, they're all below 5, I would say, right? And maybe the sodium is high, but the thing is that the sodium is not polyvalent, right? So you remember in the discussion or in definition of the total hardness, right? It only includes the polyvalent ions, mainly because all of these ions, when they form carbonate, they are sediments. They will settle down in water. But for sodium or potassium, this is always soluble, right? This is not a sedimentation. So because of that, we don't even need to consider the sodium or potassium, right? So in this way, you can see basically the hardness of the water is just mainly contributed by the calcium and magnesium. Okay, so in that case, you can just ignore all of the terms, right? Because their values is too small. This applies for all the water sample that we can see from our nature, right? So you can just use these numbers and then basically solve what is the hardness, what is the water hardness in terms of mole per liter. Okay, so let me see what the right answer.
Professor?
Yes?
So when we're doing problems like for the homework and it's like, it gives us a chart like this with all the different concentrations of minerals that are in the water. If we're just asked to find the hardness, all we have to consider is the calcium and magnesium ions.
Yes, yes, that's what I mean. Yeah. Any questions? Yeah. So basically, if you want to do more, be more accurate, you can also consider the others. But the thing is that their concentrations are, in general, I'd say most of the time, are too low. So their contribution to the hardness is, yeah, they're negligible. Okay. So if you plug in these numbers, you'll see that the answer here will first be 3.35 millimole per liter, right? And then we say that for the hardness, we want to show that as calcium carbonate, right? With this earlier example here, you see 2 millimole per liter represents 200 milligram per liter as calcium carbonate, right? So which means that you just need to multiply this number by 100 to get 335 milligram per liter as calcium carbonate. Okay, so this is how we can determine the hardness of the water. Any questions until now? Good. Okay. Yeah. So then what is the actual situation? So what about the water we have in our home, right? So as you can see here, this is basically simplifying the calculation of the total hardness. Right now we can just consider these two, right? So in our home, you can see that basically for the EPA standards, they will categorize or classify water into a different hardness level based on this concentration as calcium carbonate. Okay, so if it's below 60, right? I think in the video it was saying 61, which is not far away from 60, right? So you can call them as soft or slightly hard. If it's above 60, then you're basically in the moderately hard, hard, or very hard. So if you check the water data for Miami-Dade County, you will see that the water hardness, remember that is around 40 to 80 milligram per liter as calcium carbonate. So we're in the range of slightly hard and moderately hard range. Okay, this is not saying that water is bad for our health. Actually, at this hardness level, you probably even won't notice any white scales getting formed in your water kettle or anything, right? But if you think about if you use a water softener at your home, so for example, something like this, right? So actually there are options for you to choose how much you want to soften your water. So there is a number, there's a value that you can put in to see or to set your designated or your desired hardness. Okay, so in general, for these instruments or for these machines, their default value is 20 milligram per liter as calcium carbonate. Okay, so basically for these machines, right, they will put the water into, let's say, the soft or slightly hard range. Okay, so in this way, you can actually not only it's for your, I would say the impact on your house might be small, but the thing is that if you consider, let's say, the water heater that you use at home, let's say you use for bathing, right, use for washing, right, you don't want cold water. But once you involve the heating of the water, then the hardness becomes an issue because no one wants their pipes to be blocked by these sediments, right? So it is beneficial for you to use a water softener. Let's say just further send the water, softened water into the water heater, right? So in that way you can protect your appliances at home. Okay, so this is the standards or the classification of the water hardness, right? And then there are some more detailed, let's say, detailed classification of the water hardness. Okay, so as you probably heard from the video too, so there is a categorization of the hardness into different types, right? There is a temporary hardness, or what we call the carbonate hardness. And there's also a non-carbonate hardness, or what people call the permanent hardness. Okay, non-carbonate hardness. So basically, this is just splitting the total hardness into two, right? So into the carbonate hardness, let's say CH here, and then the non-carbonate hardness, NCH. So what is the difference? Basically, for the carbonate hardness, they are just these calcium bicarbonate, okay, or magnesium bicarbonate. We said that these are the common ions or mineral ions that exist in the water. But if you think about the calcium or magnesium, basically they can bind with any anions, right? For example, they can bind with sulfate ions or chloride ions, right? So in that case, you can have calcium sulfate or calcium chloride in your water. So we said that for softening the water in industry, right, what people do is we put in the calcium hydroxide. Again, going back to the reactions we discussed here, right? So we're using this limestone baked product to deal with that, right? It definitely works for the calcium bicarbonate, right? You see we form this sedimentation. But what happens if we have calcium chloride? Okay, so if we have calcium chloride, just look at these two reactants. Okay, so they are not going to react with each other. They're not forming any sediments, right? So we cannot use these the limestone method to deal with that hardness anymore, right? So in this scenario, we have to use some other methods. And because of that, we have to quantify what is the amount of the non-carbonate hardness, right? So we can use some other chemicals to deal with this permanent hardness in the water. Okay, so coming back to the definition here, right? So you can have the carbonate hardness. So carbonate hardness are the calcium and magnesium ions that are bonded with the bicarbonate ions, and the non-carbonate hardness are these ions that are bonded with the sulfate or the chloride. So basically, they cannot be removed by just putting calcium hydroxide into the water. Okay, So because of that, you can split the total hardness into the carbonate hardness and non-carbonate hardness, right? And in industry, when we were trying to deal with the hardness ions, we have to quantify how much is this and how much is this. And then for the carbonate hardness, we will put in the calcium hydroxide to deal with that. And for the non-carbonate hardness, we're going to use some other chemicals. For example, the soda. Okay, we can put in soda to deal with the non-carbonate hardness. We're going to talk about the reaction later on. All right. So because of this a little bit more complexity in there, so people created this graph called the bar graph to show the relationship between the carbonate hardness and non-carbonate hardness. So basically that shows the relationship between total hardness, carbonate hardness, and non-carbonate hardness. Okay, so the way the carbonate or the bar graph looks like is here. Okay, so the way people do that is we will first draw all the cations. So basically the positive ions in the first row, in the first bar. Okay, and also we will convert the unit into, let's say, the as calcium carbonate. So for example, in the short question that we had, we said that the calcium ion and the magnesium ion has the total molarity of 2 millimole per liter, right? For example, if one has 1 millimole, the other one has 1, then we're just going to draw the first bar, the top bar, showing this relationship, right? Calcium here and then magnesium here. And then on the left-hand side, that represents 0. On the right-hand side, this represents 200 milligram per liter as calcium carbonate. Okay, so this is a cation. And we'll also draw a bar for the anion. Okay, so the anion will be the bicarbonate ions, right? There can be chloride ion, there can be sulfate ion. Okay, but eventually, because of the stoichiometry or because of the charge neutrality, if you draw these two bars out, they're going to have the same length, right? Because the charge is neutral. You're not going to have, let's say, more anions than the cations or more cations than the anions, right? So you have, right, and then let's say some other ions. So in this way, you can see or visualize the carbonate hardness and non-carbonate hardness more easily. So for example, in this scenario, let's say we just look at this plot here. Right, so you have basically calcium here, magnesium here, bicarbonate here, chloride here, right? So then if I ask you what is the carbonate hardness, right? So carbonate hardness is just contributed by the bicarbonate ions. So because of that, here, this range will be the carbonate hardness, right? Because this amount of the cations are bonded to this amount of the bicarbonate ions. These are the carbonate hardness, right? And the remaining part, this is the non-carbonate hardness. And if we ask you what is the total hardness, then the total hardness is just the summation of these ion concentration. This is the total hardness, right? This is exactly what's shown in this upper plot, right? Okay, so this is this plot. But there can also be a scenario, let's say the water has too much of this bicarbonate ions, okay? For example, the water also has sodium ions, right? The sodium ions or ammonium ions, right? So there is just too much amount of this bicarbonate ions that the bicarbonate is just so represents such a large concentration. Okay, so under this situation, you can see the bicarbonate ions are neutralized by the calcium ion, magnesium ion, and some extra ions, like the sodium ions. So now if we ask, where is the carbonate hardness, right? So the carbonate hardness is just the ones or these ions that are bonded with bicarbonate ions. So that's going to be this length here, right? Which is the carbonate hardness, right? And there's no non-carbonate hardness, mainly because these ions are not bonded with a chloride or sulfate. Okay, so because of that, the total hardness is also represented by this distance here. Okay. Any questions until here? I know we're getting a little bit more onto the classifications of the hardness. Are we good? So you probably already look at the homework problems. So I think maybe there is one problem asking you to draw the bar graph for these different types of ions. So basically, we're trying to represent two scenarios. So one scenario is that water has very few bicarbonate ions. And then another scenario is that you have too much of bicarbonate ions, right? So under these two situations, then you have a different relationship between the total hardness, carbonate hardness, and non-carbonate hardness. Okay, so more detailed speaking, if you have less or if you have fewer bicarbonate ions, then basically you have TH equals CH plus NCH. But if you have too much of the bicarbonate ion, then you just have this TH equals CH. Okay, and NCH equals 0. Okay,
Professor,
yes.
What ions count as non-carbonate ions? Like when we're calculating that quantity, what ions like in a table like that should clue us into like, okay, this will be part of the NCH.
So are you talking about the anions?
Yeah.
Yeah, so they can include, let's say, chloride or the, for example, the sulfate, right, or nitrate. Okay, but in general, I would say that we just need to calculate based on the bicarbonate ion concentration. Okay, so because let's say if you have a water sample, right, you have these cation concentration already measured. Okay, so you can draw the first plot. You can draw the first bar, right? It's going to look like this. And then for the anions, if you know what's the concentration of the bicarbonate ions, right? You can draw its corresponding length, right? Let's say if it has a length like this, okay? So then for the rest of them, we just don't care because they're not, I would say they're not contributing to the, let's say, for the rest of them, they're just bounded with these hardness ions and they represent the non-carbonate hardness. Okay. And then this part represents the carbonate hardness. Does that help a little bit?
So I get for the calculating the total hardness, that's just the calcium and magnesium ions.
Yes.
So if we're gonna just calculate the that like HCO3 portion of the bar graph, and then we can just subtract that from the total hardness.
Exactly.
So how would you calculate that then?
You mean how do you calculate this part? Or this part?
Yes, the carbonate hardness.
Okay, yeah, and for this part, you will do the so generally they will give you what is the mass concentration. They'll give you the mass concentration of bicarbonate ion. So here, yeah, this is I think it's an example problem on your textbook. So yeah, basically here you will see, yeah, we do these measurements. Okay, we have this measurement of the bicarbonate ion concentration, right? And then you can convert that into the concentration as calcium carbonate.
Got it. Okay, I didn't realize that was a quantity that they just gave you. I thought to calculate it.
Yeah, that's going to be given. But you can see that if you have this quantity here, and then you know the total hardness, right? And then you can calculate what is non-carbonate hardness, right? Because yeah, basically we won't care about these ions. Okay. All right. So since we got this problem, so why don't we just quickly go over this problem and see Yeah, it's asking for what is the total hardness. Okay. All right. So to basically, it's asking for the total hardness, the carbonate hardness, and then the alkalinity. Right. So alkalinity is something we covered much earlier in the class, right? So let's just focus on the total hardness and carbonate hardness. So to do this calculation here, we'll have to rely on the bar plot or the bar graph, right? So if you have the calcium and magnesium, right, you have the mass concentration. We introduced how we can convert that to concentration or the hardness as calcium carbonate, right? Or milligram per liter as calcium carbonate. So what we'll do is we'll use this number, divide by the molecular weight, right? That is happens to be 40, right? Mole, gram per mole, right? This is milligram per liter, right? You will get 1 millimole per liter, right? And this is further 100 milligram per liter as calcium carbonate, right? And similarly for the magnesium, right? You can do or use this number, 10 milligram per liter, divide that by the molecular weight, that's 24 gram per mole. And then you can find out that this is going to be 0.417 millimole per liter, which is 41.7 milligram per liter as calcium carbonate. Okay, so you have these two values, then you can draw the first bar, right? The first bar is going to contain the cations, right? The calcium ion, and then the magnesium ion. And then it's going to have a total value of 141.7 milligram per liter. Okay, so this is the top bar, right? And then we need to draw the lower bar. Okay, so lower bar, we know that due to the charge neutrality, it's going to look like this, right? And then you have the bicarbonate ion. Okay, so bicarbonate ion concentration in here. Okay, so how do we convert this anion concentration to calcium carbonate or the milligram per liter as calcium carbonate? Okay, so first we also need to convert this to a molar concentration. So what we'll do is we'll use this 110 milligram per liter and then divide that by the molecular weight of the bicarbonate ion, right? So for the bicarbonate ion, if you write that out, HCO3, right? And this is going to have a molecular weight of 1 plus 12 plus 3 multiplied by 16, which is 61 gram per mole. So you will divide this 110 milligram per liter by that 61 gram per mole to get a molar concentration for the bicarbonate ion. But the thing is that if we want to convert that to calcium carbonate, we have to look at the stoichiometry. We cannot directly use this value here because if you go back to the equation for neutralizing these mineral ions, you see actually two number of the bicarbonate ion is going to correspond with one number of the calcium carbonate. Okay, so for this positive ion, that has a 1-to-1 ratio. But for the bicarbonate ion, that's 2-to-1 ratio. Okay, so because of that, you need to divide the molar concentration of the bicarbonate ion by 2 to get the corresponding calcium carbonate. Okay, so basically here, we'll further divide this value by 2, right? And then multiply by 100. That is the molecular weight of the calcium carbonate. Okay, so you're going to have, let's say here you have 100 gram per mole, which is the molecular weight of the calcium carbonate. Okay, so here then you will have the value of, let's see. You have the value of 90.2 milligram per liter as calcium carbonate. So basically here, for the lower graph, you're going to have bicarbonate ion here. And then the rest of them are just, let's say, the sulfate or the chloride ions. Okay, so now if I ask you what is the total hardness, then the total hardness we know that is 141.7. And then the carbonate hardness, that is going to be 90.2 milligram per liter as calcium carbonate, right? And then the non-carbonate hardness is going to be 141.7 minus 90.2, right? You're going to have the corresponding value for the non-carbonate hardness. Okay, so basically, based on the ionic concentrations, we can find out the different proportions of the hardness ions and then deal with them separately, right? So finally, here, this is the processing, or this is the processes where we deal with the hardness, right? For the carbonate hardness, okay, or the ones that are bonded with the bicarbonate ions, right? So we will introduce these calcium hydroxide to basically neutralize these minerals, right? To form the sedimentations and then to get rid of them. But for the non-carbonate hardness, right, as we introduced, for example, the calcium sulfate or calcium chloride, then we have to use the soda ash, right? So basically to introduce this carbonate ions in there, right, to neutralize the calcium ions, right, to get these hardness ions to settle down. All right. So basically, this is the reason why we need to separate them, because the carbonate hardness and non-carbonate hardness are removed with different methods, right? If you know what is the quantity for the carbonate hardness and non-carbonate hardness, then you can find the raw material, the quantity of the raw material to deal with them separately. Okay. So finally, this is the basically for the removal of the hardness that we show here, right? This is for industrial water treatment. This is talking about large quantity of water. Let's say if we have a water treatment facility that's mainly doing extracting the groundwater for treatment, then people will use this method, right? But if you're just talking about the residential usage or the residential softening of the water, then people actually use this cation exchange softening. So this is exactly how the water softener you use at home to deal with these hardness ions. So what happens is that they have these resin, right? So these resin are made with special type of material that can bind with the ions based on the surface charge. Okay, so basically, if you have initially these resin balls or these resin tiny particles, they're bonded with the sodium ion. Okay, so once they meet with the water that has hardness ions, then these ions are going to get exchanged. So the resin is basically a very easy to get bonded with these hardness ions. Okay, so after some time, we have to regenerate these resin particles by exposing them under a high concentration of the sodium ion. So this is why you need to use the salt, right? You need to purchase salt and then put it into the water softener, because the salt in the water softener are getting dissolved to form a high concentration of the sodium chloride. And then this high concentration of sodium chloride actually go through this ion exchange process to get rid of the calcium ions and then further go to the sewer, right? You just dump the extra water and then this can regenerate it, and then so that you can use the resin again. So normally these water softener are very reliable. So for example, the one that I used at my home, it was installed maybe 20 years ago. It's still working. So you can just regenerate these, right? And then all you need to do is to purchase the salt and then monitor the level of the salt for reducing the softening ions, right? Okay. So this is some short introduction of the salt that we use for the water softener, right? You can use sodium or the potassium to deal with the ions in there. So I think that's it for this class. So do remember to send me the questions that you might have regarding the preparation of the exam, right? So we can go over these questions. I mean, on our Tuesday's class. Okay, so I'll send you that Google form later on, so you guys can fill in the information. Okay, any questions? We good?
Yep. Thank you.
Thank
Okay,
you.
yeah, great.
Thank
All right,
you.
see you next week.
Thank you. Have a good day.
Yeah, bye.